Okay, so a couple of reminders. I think people have already started submitting their team names. Thanks for that. Those are due at the end of this week. So just looking for 2 students a team for this final project. If you're having trouble finding a teammate, I posted a spreadsheet on Canvas that you can sort of use as a clearinghouse for who's looking for a teammate, and or I mean, just generally, since there's only two, who's looking for a teammate. And then once you form that team, then a week later, and these are due on Saturday. There's a little bit of flexibility there if they don't end up coming in, but I'll be having a look. Once as these come in, I'll form groups on Canvas. So this will be the first group assignment. And that again, due Saturday, there's a list of candidate algorithms that we won't cover in the class that are also nature inspired. If there's another one you've heard of or that you'd like to further investigate that you think is not covered already in class, like a significant extension of something that we've done in class or just not on the list, that's fine. You can propose your own choice with some justification. I'll review those and then give them my check mark, and then the next thing after that is the short proposal where basically you're not only saying what algorithm you want to do, but you're going to say that we're going to study chaotic catfish particle swarm optimization, and we're going to, in order to demonstrate how it works, we're going to use a normal particle swarm optimization and chaotic catfish in a experimental optimization of a video game or something like that. So you basically, you don't have to tell me all the details, but basically what's your general plan of like, well, what am I going to just optimize a numerical function? And I have listed along with that document, so this might be more appropriate for here, you also find some sample test functions. So a lot of times when people do optimization algorithms, it's popular for people now that, there's a gym, for example. So now there's a bunch of simulation options that people will often use, but you can still use numerical optimization. And there's sort of some common benchmarks, some test functions, and I've listed a bunch of those. I have a sheet that actually I think links to a page that has a bunch of those. But if you just want to do, a complex multivariate numerical optimization, kind of like in a more complex version of what we did with Mini Project One, that's totally fine. And then look at that list. But if you don't want to do that, if you want to have it like, train it to play Tetris or something like that, that's also fine. And plenty of people have done those sorts of things. Or if you have a totally different, I think, if you have something, if for your own research, maybe you're designing multi-jointed robots in simulation. And so you test a bunch of designs and how well they do certain things. And there's a bunch of parameters that you can manually tune. And you say, well, I want to just have an algorithm tune those. So then I'll go through and have the algorithm choose a bunch of ones and then run my robot through and see how quickly it can move an object from point A to point B. And maybe it's a planning algorithm and coming up with these new paths to get from point A to point B. And there's all of these different parameters you could tune. And rather than you tuning it, have the algorithm tune it. And then, how, maybe you wanted the shortest path or the lightest arm or the cheapest or whatever, or maybe multiple objectives. Then, that's the type of thing that, all of these are, a bunch of things are out there. It just basically in the end, what the final report that you and your partner will submit at the end of the semester is just going to be this little 4-page kind of extended abstract where you say, here is a sophisticated algorithm. Here is a test case we've used to feature some features of the algorithm. Here is how it worked for that test case and something that it demonstrated about that algorithm that came out of that test case. And so, look, it's particularly good at finding solutions to this that maybe an off-the-shelf numerical optimizer wasn't able to do, something like that. So that's kind of the vision. It's very open-ended. It's just in the end, we're really just trying to sort of give you an opportunity to find information about a sophisticated state-of-the-art nature-inspired algorithm, drill down into figuring out how it works and how you apply it, and then demonstrate that you were able to apply it and show off something interesting that someone who hasn't gone through that process would be able to pick up and say, oh, okay, so even though I don't know how to implement that algorithm, I can see that the purpose of that algorithm is, it's trying to improve X or Y. When eventually, as maybe an example of that, eventually we will get to particle swarm optimization, and I'll talk about how particle swarm optimization was was formed in part because genetic algorithms were so bad at optimizing neural networks at the time. And now, if you've ever optimized a neural network, you know that you've got these regularization components that you add in, these penalties, and we're going to draw an analogy between that and particle swarm optimization. So you could imagine, I mean, we're going to cover that algorithm, so you wouldn't do, but if I was to write a little 4-page write-up of that, I might show that, okay, so I have this relatively simple genetic or neural network that I want to train, and I'm going to train it with a GA, and I might train it with a PSO, and I see that if I train it with a PSO, I get maybe more stable, more reliable solutions. Maybe I get quicker convergence, et cetera, et cetera. So that would be comparing those two, the benchmark, the baseline being the GA, and the PSO being the new innovation and why it does what it does. So that's kind of an example of the types of things that you might show, but it's pretty much open to it. And so in your proposal, that's what you're going to sort of let me know, like what your plan is, and then I'll give you feedback on that. And so come back and say, well, I think that's really ambitious. Maybe let's tone it down a little bit, or that seems like what you're showing isn't really anything that is that surprising. So you kind of want in your final project to show the reader something that needs justification through an actual experiment, but is also scoped to the short time that you have to do the project. And that's what I'm going to try to give feedback on when you turn that in April. Otherwise, in the shorter term, muddiest point, concept check, and another mini project opportunity. I think I saw that there's like 3 mini projects. The grader still is trying to grade on mini project 3. And then I think 4 has got like 4. So once he gets those graded, he'll usually ping me, and then I'll post them. So those are coming, the 3 and 4. Okay, any questions about any of that? Okay, I'm just going to see if I can get this camera to work one more time. And if not, I'll just give up. Looks like it's frozen. All right. Okay. All right. Well, in the video of this, you'll just see the lectern a lot. All right, so we are shifting on. So we finished Unit 4. Those niche preserving algorithms, if you go back and look at the PDF of the notes from the class from that, I added a page in the end where I kind of summarized the computational complexity for each one of those. Some of you in your muddiest points said that you're having trouble sort of seeing where some of those computational numbers, or those complexity numbers came from, and I tried to respond to that in the muddiest points. I'm about halfway through the muddiest points, and once I post those, you'll see that. But I'm not too concerned that you can tell that, well, that that one particular one is going to be in squared, or maybe like restricted tournament selection will be in W. I'm not too worried about that, but the biggest point that I want you to take away from it is that because niche preserving algorithms require each individual to calculate its distance to every other individual, if you've got lots and lots of individuals, then that doesn't scale very well. So at worst case, you'd expect it to be, n squared. And if you try to do something super clever, that you could actually do even worse than that. But so you don't want to be worse than n squared. Are there ways that you can achieve the same sort of clustering, the same sort of spreading individuals out without needing all of those pairwise connections? And there are clever things you can do with data structures. So if I calculate a distance between me and you, if I then go around, if I'm iterating through the population, I hit you, then if I haven't moved and you haven't moved, then you probably don't need to recalculate that distance. And so there are ways in which you can structure individuals in these kind of agent-based populations so that you don't have to do quite as much calculations, but it's still, kind of costly. And so that's kind of the cost of keeping this diversity. So diversity is non-trivial to maintain in evolutionary algorithms. And that's kind of the big thing that I was kind of stressed there. You don't get it for free. And if you want to enforce it, it may cost you a lot in terms of runtime in those so exactly how much it costs is going to vary. And again, I'm not worried about you being able to calculate all those, but if you at least get the idea that at a worst case, if you have to do all of those pairwise combinations every single time you go through an iteration of your meta heuristic, that's potentially pretty bad. So that's the idea there. But today, this unit, we're going to start now on flipping from fitness landscapes to energy landscapes. So from biologically inspired optimization algorithms to physics inspired. And this will allow us to also talk about some things you see in machine learning, at least classical machine learning, like MaxEnt methods and so on. So let's get to that. So our entry point here is that, in this section of the unit, we are trying to motivate simulated annealing. This very popular, still today, very popular optimization meta heuristic. And we're trying to sort of see, how do you build simulated annealing? Where does it come from? And how does it relate to other things that you might see as a data scientist, as a computer scientist? So what is simulated annealing? So this, like I said, it's simulated annealing. I'm going to call it SA. Maybe red is not such a great color. So SA. So this is very popular, very successful optimization meta heuristic. It is not an evolutionary meta heuristic. This is, in fact, the traditional SA is just a single agent running around a landscape. So it's not multiple agents at all. And the SA is actually even has hardware implementations now. So well, the essay that we'll be talking about is primarily going to be viewed as something you implement in software, but essay is so successful that in order to speed it up even more, because it's used so much, there are groups that have used, they're like, basically, FPGAs. There's even quantum groups. So D-Wave, for example, this is a quantum annealer. And then there's also, kind of bridging a little bit towards the bio-inspired, there's Loihi in solutions. So this is an Intel neuromorphic platform. So basically, there's a chip, Loihi, which we'll get into what neuromorphics are later in the semester, but this is a type of neural network that is built on spiking neurons. You can buy, Intel has a chip you can buy that has a bunch of these spiking neurons connected together, and you can implement a simulated annealer with spiking neurons in hardware. It runs very fast. There are just more conventional hardware solutions, just using good old-fashioned hardware, and then, like I said, there are these quantum solutions. And so some of the first quantum computers that came out, if you learn about quantum computing, eventually everybody's just going to have to know a little bit about quantum computing. Quantum computing has gotten kind of less interesting now that we have post-quantum cryptography, so you don't have to worry about quantum breaking your crypto anymore. You just have to wait. I mean, you can go into Chrome right now and turn on post-quantum cryptography, and then you're done. So all of this crap about factoring numbers is not quite as interesting anymore, but there's still like 2 or 3 applications that quantum might be good at once upon a time in the future. But those are based on these 2 types of systems: gate-based systems and effectively these annealing-based systems. And so the first people to kind of come out and say they had a quantum computer with lots of qubits was this D-Wave company. And I think they even had somebody a couple of years ago came and give a talk at ASU or Inside Sky. And most of the real diehard quantum people say this isn't quantum computing because it's not gate-based quantum computing. And the gate-based quantum computing is we actually put together these so-called billiard ball computers where you have like gates put together just like a digital logic circuit. But the way quantum annealers work is they basically will implement exactly what we're going to talk about in this unit, but they do it leveraging quantum mechanical effects that allow qubits to move around like the particles that we are going to talk about in this unit. And it's just sort of a way to speed up that. So this D-Wave product that you may hear about, this is like the most number of qubits you can find is through this D-Wave product, because it isn't the problem with these gate-based solutions that you see coming out of now. Amazon just released a gate-based solution, and so did Google and Microsoft, and they're all going to be gates in the cloud. So these, you're going to buy cloud resources, but those require quantum error correction. It's really hard to scale up. That's why they're like limited to whatever 60 qubits or something like that. And these are a lot higher than that, but they do something very different. So that's a completely different type of quantum. And it basically does exactly what, again, we're going to talk about in this unit. So once you've learned this unit, you can talk quantum annealing. But it's and all of these things are just sort of, again, ways to do optimization. So before we said we're going to take your optimization objective and we're going to turn it into a fitness function, and then let a little simulated community of organisms crawl around and see what shakes out as the most fit. Here, we're going to turn your fitness objective into an energy landscape and then allow a simulated physical system to shake out at the lowest energy level, and that will be your optimal solution. So that's kind of the picture of where we're going here. So toward that end, if we have a real physical system, so this is just background here, so background, physical system. At a given temperature, and I'll just call that temperature uppercase T, then that that could be this chair. This is that's what I mean by physical system. It's like the whole of this chair, the whole of that desk, me. That's what I mean, a physical system at a particular temperature. That system can be described as having many different so-called microstates. So you have I'll say many microscopic components that together can instantiate many different microstates. So many microscopic components or degrees of freedom that give rise to many microstates. And so what I mean by that is that that chair is sitting there, but it is made up of a whole bunch of molecules. And those molecules, some of them are jiggling faster than others. So at any instant in time, there's a whole many Avogadro's number times microscopic elements inside this chair that are all doing their own thing. And the state of the chair is the kind of Cartesian product of all of the little tiny states of each one of those microscopic components. So this chair, as it sits here, it looks like it's one thing, but it's one thing that under the covers can be in a gazillion different configurations. All of those configurations look the same to you. That's the macro state of this chair, is that, this chair is in kind of there's like an equivalence class of those microstates. But the thing that is the chair is a whole bunch of different ways that those molecules can jiggle around. And from second to second, it moves from microstate to microstate. So, if as this just sits here due to thermal agitation, then a slightly more active set of molecules here might then trade their momentum, and then now you might have a slightly more active set of molecules somewhere else in the chair. So the chair is constantly jiggling from one position to another position to another position, and it's moving through all these different microstates. But to us, we just look at this as one macrostate that we would call black chair. And so That's what we mean by a physical system at a given temperature. Underneath it all, this roiling symphony of microscopic elements that give rise to microscopic or microstates. Now, some microstates are at higher energy than others. So the idea here is that if you heat the chair up, then you're going to excite these microscopic components to start moving a little bit more. And you are going to make some microscopic or some microstates more accessible by heating the chair up. But at the given ambient, like the room is not at absolute zero. There is some ambient temperature, there's some energy available in the room that will cause this chair to jiggle from lower microstates to slightly higher energy microstates and then back down to lower. And so it will tend to be at lower energy microstates because things tend to go lower, but it will occasionally, because it's thermally agitated by the temperature of the room, bump up to slightly higher microstates. So there's this constant jiggle, and that's just constantly going on inside that chair. So some microstates are going to be at lower or higher energy than others, and the temperature T allows the microstate to sometimes move into higher energy, I'll say higher E configurations, and then back down. So what I'm getting at here is that I hope you can imagine that we could create a probability distribution over microstates where the lower energy microstates would be far more common than the higher energy microstates. But there would be some probability mass that would be clustered into the higher energy microstates. And as the chair gets hotter, then that distribution would get flatter and allow you access to more and more high energy microstates. That's something called the Boltzmann distribution, which we're going to get to. That's what we're trying to build up to. But that's the picture I want you to be building in your head, is that in any physical system, the system underneath it all, the underpinnings of what makes up this chair, that desk, me, you, is a set of microstates that they're naturally sitting close to their lowest energy, but due to thermal agitation, they have access to higher energies. And with more and more heat, with more and more temperature, then you'll get access to even more other states. And it's this idea of constantly being able to jiggle through states and sometimes being able to access other states that we're going to turn into a search process the same way we turned into the process of evolution into a search process. Okay. So, question about that. All right, that's the conceptual model. So, how do we make this a little more concrete? Well, there's this thing called Boltzmann's constant. Okay. And what, I don't know why I underlined that. And what Boltzmann's constant does is it converts temperature into the energetic budget that is sort of accessible to those microstates. So when we talk about Boltzmann's constant, then you can what it basically it says. So to physicists, temperature is energy, and it's proportional. The amount of energy in a system is proportional to the temperature of the system. And so Boltzmann's constant is the constant of proportionality. So the average energy in a system, so this is I'll do this, I'll write it this way. This is average energy is just equal to Boltzmann's constant times the temperature. So in other words, the average energy is proportional to, so that's my symbol for proportional to, um, the temperature. So if you're basically at a microstate, then you can kind of figure out that if a nearby microstate is more than kT higher energy than your current state, then it's unlikely that you're going to spontaneously get there. So this is sort of how much energy is just sitting in the chair. It's its budget that it can spend on temporary excursions to higher energy microstates. And so if the microstate is farther away than that, then it's unlikely to get there. If it's less than that, then it'll probably visit there pretty often. So that's why in so many, if you ever take a thermodynamics class, you'll see so many things with KT in them because KT determines how mobile the microstate is in any physical system. So it is a little bit like the drift barrier in the natural case or in the biological case, where that kind of determined how much you sort of wiggle away from your current equilibrium. That determines how much you wiggle away from wherever you're currently standing in. So this will be maybe a little easier as I draw a picture of this. But so, I mean, basically, to summarize in words before I draw it out, system will more easily move up energy gradients if delta E is less than KT, where this is the increase in energy up the gradient. So if you're sitting at the bottom of an energy potential, you're at the bottom of a well, and you look up the well, then it's kind of like if we're talking about gravitational potential, it's like you have a certain amount of as you move around, eventually you get so high on that well that you just don't have enough energy to keep climbing up this slope, and you kind of fall back down. And so that is kind of this threshold where it'll be very easy for you to access certain heights low at the bottom of the well, and above that, then it's just very difficult for you to get there. Even with a running start, you're just not going to be able to sort of get there. And that's the kind of energy budget on KT. That's the kind of calories that are stuck inside that particle at the bottom of there that are just from the ambient temperature. So if you, and the idea here then is if you heat the system to high temperature, then you get more access to these states. And so you'll often be far from minimum energy. And then likewise, if you cool to low T, you can catch system, I'll say can catch system in suboptimum, I'll say in suboptima, and energetic, maybe that's a little, I'll move this over. In energetic suboptima. So the idea here, and this is what is going to be the key point in simulated annealing, is that if you heat a system to very high temperature, then you sort of allow its microstates access to a bunch of different configurations that they just simply couldn't get to before. And then if you rapidly cool them down, then if those new microstates happen to be in another energetic well, another potential well, then it's possible you can trap them in sort of a local optima away from the place that they were before. Or you might be able to move them farther down their hill. And so this annealing process this is what physical annealing is, which we'll describe here in more detail, is this idea that if you have an impure substance, if you heat it up and then slowly cool it down, heating it up allows it to find the sort of more pure crystallized, a regular configuration that is really at low energy. And once it finds it, then if you slowly cool it down, then you can keep it there. And then that will get you the more pure configuration. And so that's what annealing is. That's one of the ways in which you can make a stronger material, a more pure material, and so on, is just by heating it up and slowly cooling it down. And that's what's kind of going on behind the scenes. So if I want to draw that out, and then I'll stop for questions here. So if this is our energetic landscape, so on this axis, we've got energy. And on this axis, I'm going to say we've got our microstate configuration. And then, so we've got this energetic landscape that, has a bunch of these little valleys, something like that. So this is our lowest energy state here. The lowest energy configuration. So this is a lot like if you imagine a bunch of fine particulate matter sitting at the bottom of a plastic jug or something like that. It just sits there, but if you jiggle the jug a little bit, then you get a bunch that's sort of floating around in the air. And eventually it will settle back down to this lowest energy configuration. But with that, whenever there's a little bit of energy in there, then it can move away from that. And it might even get stuck in other pits in that jug. So there might be other little divots in that jug that it might get stuck in. And if you are clever about how you kind of shake it up and then let it cool down, then you can get them back all at the bottom of the jug. But if you just randomly shake it up, then they might get stuck in the handle of the jug or something like that. So that's kind of the picture that we have here. So you have this alternative configuration over here. So this is kind of a local suboptima. And so from here, there is this barrier that it has to get over in order to find the next well. So I can call this delta E. And so if it has enough energy, it will have the ability to get up over that hill and down to this hill. But the amount of energy that it has to actually move around is described by temperature. And so that will be its average energy is equal to KT. So if you're sitting in this microstate, like you've got particles stuck in that little handle of the jug that isn't quite at the bottom of the jug, but it has a little divot that's just keeping them there, then if you shake them hard enough, they'll get out of the handle and there's a chance that they'll fall back to the bottom of the jug. But if you don't shake them hard enough, then they'll just get a little higher in the handle, then to come back down and settle back down in the handle. So that's the idea here, is that we've plotted out different places where those little particles can be inside of that hollow jug with the little handle divot in it. And so this is a configuration where maybe some are at the bottom of the jug and some are the handle. Maybe this configuration where they're all in the handle, and this configuration where they're all at the bottom of the jug. That's the lowest energy configuration, lowest, everything lowest gravity, or gravity is the same, but they're at the lowest height. But they can get stuck there, and the amount of energy they need to get unstuck, if that is, we'll say, if that is greater than temperature. So again, physicists often in thermo, if they get really abstract, they'll just forget that temperature and energy are different things, and they might even just start using them interchangeably here. So if the temperature is not enough to get over the energetic barrier, then you just get stuck there. There still is a chance, because it's a long-tailed distribution. There's a chance that at a lower energy that you'll be able to get over there. This is just the average energy. But most of the time, you're not going to find yourself moving to another intermediate microstate. So this up here, I could draw, this is some um, the intermediate microstate that is spontaneously visited. And so that is going to be less common if your average energy is less than that barrier. Question. Well, the bottom, we're sort of assuming there is an energetic landscape that we know of. We're trying to find. So we ultimately, when we develop this into an algorithm, we are going to design our physical system so the energy of each configuration is proportional to a fitness object. I don't know what's a fitness, an optimization objective that we want to minimize. And so you're going to have a function like I would like to know what value of x, where x is a vector, that minimizes s. I'm going to show you how to design a probability distribution that if you know how to sample from it, then it over time will be very likely to find the minimum of that. But at any instant, I don't know where it is. Kind of all I know is that the that for I'll know that if I want to stray, so basically, if this becomes my x vector and I propose moving in this direction, I'll be able to evaluate my optimization objective here and my optimization objective here. And I can say that's a really big energy jump. I'm not going to let you do that. But if instead it proposes to go here, I'll say, well, that's a very small energy jump. I'm going to allow you to search over there. And that's kind of how this algorithm's going to be formed here. And so if we heat the algorithm up, then I'm then going to allow you to move anywhere throughout the space. And so that will allow you to get over this hump, but it also will allow you to get way over here and way over here. So it's going to be this combination of how we heat things up and then cool things down slowly to sort of guarantee that we don't settle down into one of these humps that we finally find it here. So that's where we're going with it. So we're not trying to predict exactly, like we want to predict for a given energy, how far away do we move from a starting position. We're not trying to predict exactly what the shape of we're trying to use that then to search this space so that we eventually settle down at a lower point than we started in. Yeah, so that's a good point. So at any particular, it is possible when you have these multi-well potentials, if you know the energy in the system, you can calculate how long on average it will take until you move from this well to this well. It actually comes out of Markov processes, really. So you can model the position here as a Brownian walk, and where there's it's sort of harder to move uphill, but it is still possible. And so you kind of have it's what we call a drift diffusion process, where you have a little bit of a drift component. There's sort of an average tendency, but you also have noise on top of that. The noise correlates to the temperature. The drift correlates to sort of the shape of this well. So you're always going to drift down the well, but then the noise will kick you out from there. And these drift diffusion processes, you can plot them on other sorts of plots. Like you can say, well, I've got this is the bottom of well one, and this is the bottom of well two, and this is the position of my particle in between. And I can it sort of wanders around, and I can see how long until it hits one of these or the other. And there's ways in which you can solve for the probability distribution of that time. So that is something that is in the math and that physicists do all the time here. They do it even studying climate. So like how long, if you have an ice age and a warm Earth, then how many thousands of years until the Earth naturally just shifts from an ice age to a warm Earth, and things like that. So yeah, these double well potentials, you can do those distributions as well, and people have done that. That won't be it becomes important to when you get into really the mechanics of how well you design these algorithms, then you start worrying like convergence rates. You say, how do I speed up the convergence rates? But as we see, because we're going to use an annealing schedule where we're going to be sweeping the temperature, then it won't be as interesting to know for a given temperature how long will it take to converge. Because we'll have these kind of heuristics on like, well, we're not going to wait that long. We're sort of going to slowly, but theoretically, yes, you could actually say for optimization objectives of this particular shape, I would expect roughly this amount of iterations of my algorithm until it converges. And you probably could use the same math to do that. Just kind of thinking out loud. Okay. So any other questions about this picture? This makes sense. This is sort of what we're trying to set up. Again, this is a depiction of what happens in physical space here. So in annealing, in normal physical annealing, then we are going to heat material to recrystallization. So basically very high T. And then we are going to cool slowly, which is going to basically lower T by a schedule. And then hope we catch system in low energy configuration. That's what you do in physical systems, because lowest energy configurations, that's when you're going to have the kind of the least amount of kinks in the system, the least amount of fracture point or little stress points. It's going to be the sort of smooth. I mean, it's just like if you imagine an ice cube that's got a bunch of ridges or whatever, if you kind of heat it up until it liquefies and then freeze it slowly, then you might get a perfectly fine edge without having to Zamboni the top of it to smooth it out. And it's kind of the same idea here, where you're trying to heat this thing up so that all microstates are possible. And then if you cool it slowly, even though at high temperatures, it can be anywhere within this landscape, it will still be more likely to be at lower energy by these probability distributions, by the so-called Boltzmann distribution, is that if it can access everywhere, it'll be more likely that it's here. It'll be here more often than the other places here. So basically, if you heat this system up and then manage to sample where the microstate is, you'll actually etch out a distribution which looks like this energetic distribution. It will just spend more time frequently here. And since we're counting on it spending more time frequently here, then if we heat it up and then cool it down very, very slowly, then we're hoping that over at all temperatures, as long as we don't make this inaccessible by catching it when it's over here while it's cooling down, at all temperatures, it will spend more time here. So if we cool it slowly and slowly, more and more slowly, then we should eventually trap it so that it has no option but to settle down at this low energy state. And again, that's exactly what happens, whenever you've got, if you've got a bunch of, I don't know, pebbles or something like that in there, and you kind of jiggle them a little bit and you kind of, you sort of jiggle them fast, but kind of slow down the way, and eventually you get like a kind of the level out at that low energy configuration. So all the little faux mountains go away because those were higher energy configurations. That's what you're effectively doing, but you can do it for any material and to sort of settle their microstates down. That's annealing. Questions about that? And that's what we're going to simulate in order to build a in order to build an optimizer. So I guess I'll maybe add over here. I'm just going to take this low, well, I'll just put it over here. And I'll say then for simulated annealing, then we're going to make our energy function proportional to F, which will be an optimization objective. And that we are going to use the design a annealing schedule and then our microstate is our heuristic optimizer. So what I mean by heuristic there, going back to the basics, is somebody will say, well, how did you decide that this is the best design for your system? You had, 100 different parameters. Why did you pick these for 100 different values? And you can say, well, I put it into a simulated annealing algorithm and I heated it up and cooled it down. And I did that a couple of times and it kept coming to these values. So I figured those are probably good enough. So that was my heuristic, is that it came out of the annealing algorithm. Okay. So that's where we're going. So the key thing here is to figure out how to build a probability distribution that does this magic for us, and then how to sample from it. So what is the energy parameterized distribution that moves these microstates around? So that, and I say microstates here, that's going to be, these are candidate solutions. So remember, I said you've got in your chair, you've got a gazillion different molecules that each can be in different energy levels, different momenta, different positions. Now imagine that each one of those molecules is a decision variable. And each one of the decision variables can be in different states, just like each one of the little molecules can be in different states. That's what I mean by our microstate configuration. You can think of those here. These are your decision variables, or I'll say decision vector. And so each component of the vector can be in different states, just like each molecule of the chair can be in different states. So our microstate configurations are our candidate solutions. So just like in physics, there is a distribution that describes how microstates move around within a material at a particular temperature. We need to simulate. We need that. We say this is where the physics inspired is like physics is really good at finding low energy states. And when physics gets stuck, there's an easy way to get unstuck. It's called annealing. We heat things up, we cool them down. That's what we want, but we want it inside the computer in our designs. So how do we draw new designs so that they jiggle around like the microstates in that chair? That's what we want to design. Okay, so how do we get there? So how do we mimic the physical principles of a process? So we're motivating this Boltzmann distribution. So, you know, a question here is, what does a physical system look like at equilibrium, at a particular temperature? I'll say at T. And this is what the topic of entropy is going to now enter into the subject here. So we're going to better define entropy to sort of understand it and use it. So the idea here is that if we think about a room, so imagine I have a room like this one. I guess I probably could have just, I've got two rooms, two different times. So if I were to imagine this room, and let's say that there were some colored gas that I released into the air. And so you could now see where that gas was. And so if you were to see that that colored gas was all over here, or in another room, you'd see that it was throughout the room. From this perspective, which of these do you think is at equilibrium? Or which do you think is later in time? How many people would say this one is later in time? How many people would say this one is later in time? All right, so more hands for this one here. Why? I guess I would just say, think to your. It's hard to answer this question, but I have a feeling if I asked you to sort of say, voice, why do you think this one's later? Um, you'd say, well, it's more spread out. But why do we think more spread out is later? You know, that's kind of the fundamental question. So I guess with that, so beyond it just being sort of more spread out, I guess that's my question is, why do you think more spread out would be later in time? Yeah. But what does that mean? Why does entropy increase over time? Kind of osmosis. Yeah. And so osmosis means is diffusion. So I guess when you say kind of osmosis, I think you're sort of saying that if there's any movement in one direction, there's probably going to be the same amount of movement in the other direction. So it just kind of balances out. Yeah, I kind of like that answer. Is that if you kind of think about it, the these each one of these, this gas, each member of this gas, each little parcel of this gas, each molecule of this gas will move. It's thermally agitated. It's going to move. And so there are more ways to move away from this, and I'm going to use a new term here, macrostate, than the other macrostate. So what I'm trying to get at here is that just by random chance, so if you imagine a random movement, the random movement does not change this macrostate. And so that's kind of what we're saying is that random movement is very likely to change this macrostate. So it is, by macrostate, I mean the overall description of where all of the particles are. So we can say that there is a macrostate, there are microscopic configurations making up this chair. The macrostate is chair, but there are a lot of different ways you can build this chair. So, you can, again, jiggle things around differently in here, but it's still going to be at a macro level the same chair. If you put a bunch of pink gas up in the corner of this room, it is possible that it's going to stay there forever. That is a possibility. It is very unlikely. It is possible that it will move out toward me and then go back into the corner. That is possible, but there are very few trajectories that would allow that to happen. It is much more likely that it will move throughout the rest of the room. And once it fills the room, then at that point, it is extremely likely it will go from one room filling configuration to another, and another room filling configuration to another, and so on. It is very unlikely it'll go back into the corner. It is possible that it will go back into the corner, but it is very unlikely that it will go back into the corner. So that's kind of, the idea here is that this macrostate, another way to view this is there are fewer microstates. And here there are more microstates. So there are a bunch of microstates of gas in this room. We can bin them into macrostates. We can say these are the microstate configurations corresponding to gas everywhere in the room. These are microstate configurations corresponding to gas in the corner of a room. That will be far rarer than the one that's everywhere throughout the room. And this is entropy. Entropy is a logarithmic scaling of this count. So basically the entropy is equal to log number microstates. and we're going to call entropy, and I'll say it's proportional to, and we're going to call entropy S. And delta S is greater than 0. So this is the second law of thermodynamics. And so all that means is that if you have created a macrostate that has fewer microstates and you allow the microstates to move around randomly, then it will be much more likely for your system to move towards macrostates that have more microstates in them. So I think that should just kind of make sense that if you've defined a rare property and then you've allowed the things that constituent that make up that that system to move randomly anywhere, then it is unlikely they're going to stay with that rare property. They're going to move to the more common property. So if you have a microstate, a macrostate, a configuration that sucks up, it has a bunch of microstates in it, then just random movement is going to be more likely. If we think about the from microstate dynamics, it is equally likely for any microstate to go kind of to any other microstate. There's no preference in microstates. But because there are more microstates, it's like a dart on a dartboard. If you've got a giant area on a dartboard and a little area on a dartboard, then if you happen to hit the little area on the dartboard, that's great, that'll happen. But most of the time, it's going to be the big area on the dartboard. Or if you're just wandering around, if you paint that dartboard on the floor, if you're just wandering around randomly, if there is a very small portion of the floor that you start in, you might stay within that small portion of the floor, but it is much more likely that you're going to wander into the large portion of the floor. And then you might then wander back into the small portion, but most of the time you're going to stay in the large portion. That is the second law of thermodynamics. So we expect systems to, at their macrostate level, to exhibit kind of high entropy. We expect systems to be in distributions of microstates that correspond to these sorts of distributions, these high entropy distributions. And so when we weight our microstates to say, all right, how far away are we allowing you to get based on how much energy is in the room, then we are going to want to design that distribution to be like the high entropy one. Or another way is if I tasked you, said, here's your homework assignment, build a simulator for gas in this room. You could build a simulator where all the gas just lives in that corner. And that theoretically, and you could show me that their physics is valid or whatever. And theoretically, that wouldn't be necessarily wrong, but it would be a highly biased solution to say that I think that everything is going to sit in that corner. So can you guys wait for your next class? So the idea there is that if you're trying to build a simulator for the most likely distribution, then you want to you want to remove all that bias. And that's when we talk in machine learning about entropy, it's about bias. Maximal entropy in machine learning or data science means minimal bias. And that's what we're going to try to get to here. All right, so there are other ways that I can kind of describe this. I can actually say that this low, we're going to call this low entropy, and this is high entropy. And so another way to view low entropy microstates and macrostates is actually by how many bits of information it takes to describe the microstate, given that you know the macrostate. So a low entropy here, this means there's little info needed to describe the microstate given the macrostate. And then over here, there's much info needed for microstate given macro. So what I mean by that is if I tell you that we're in this macro state, then there are very few microstates that it could be. So you could say, oh, you're in that one where it's the pink up in the corner. Then you can say, well, there's only like 6 ways that pink could be up in the corner. Which of the 6 are you? And so at that point, if I give you 3 bits of information, I can get all 6 of those, and I've still got some information left over. Over here, there are so many different ways to be spread out and run this macro state that you need many, many bits of information in order to specify that what you are inside that macro state. So here you could say, oh, well, the gas was distributed everywhere. I'm like, well, if I need to know exactly where every single molecule was, it doesn't help me to know the gas is distributed everywhere because there's a lot of different ways the gas can be distributed everywhere. I might need, thousands of bits of information to actually specify the actual microstate of this situation here. So what we're trying to get here is there's an informational component as well here, and that as you move through time, so as time moves in this direction, what you're doing is you are losing information about the history of the system. And so here you have so much information about the history of the system, you don't need any additional information. So you can view this as additional info beyond history. So when you know the history of the system, you need very little additional info to specify how much the system, what the system state currently is in. But over time, you lose all of that history. So that's another thing that we talk about high entropy configurations. This goes along with this idea that you have low bias. So there's low bias, there's low dependence on history. So the fact that we need 1,000 bits to specify the microstates here, and only 6 or 2 bits to specify, or 3 bits to specify the microstate here, is a reflection that we have given up a lot of hidden information that is shaping the macrostate, so that now the only information left is the actual, is the raw information about the microstate. And so that's why when we're going to start next time, when I go into these maximal entropy distributions that we use in data science that will then help us build up to how we build simulated annealing, then this will be another motivation for why we seek out maximal entropy distributions. Because basically, if somebody tells you, I don't know anything about a particular distribution except that it has a minimum and a maximum, there are a gazillion different ways you can build a probabilistic distribution that has a minimum and a maximum. But the question is, which one should you build? And what I'm trying to, just like there are a bunch of different distributions for how gas can exist in this room, we want the one with the least amount of bias. We want the one that reflects only the constraints and not additional info. If somebody tells you, I want to draw a random number that is has a minimum of 0 and a maximum of 10, and you design a random number generator that looks like this, where it's going to be 0, 1, 2, and never anything more than 2, that's legal. You're going to give them a random number between 0 and 10. That is a perfectly reasonable distribution. But it's bad because it's biased, because it doesn't allow for you to fill out the whole space, and it reflects some additional assumption that was not given. Like, why would you choose one that only does 0, 1, and 2? They only said it was from 0 to 10. Why did you just decide not to populate the rest of that support? And you can say, oh, I don't know. You had an additional structure, an additional constraint in your head, and that is encoded into the low entropy macrostate. A maximal entropy macrostate gets rid of all of that, so that the only thing that defines this distribution are the constraints that are given formally. And that's why when we talk about MaxEnt, which became very popular in natural language processing, that the reason MaxEnt is used is because they want to say, we want to choose a distribution that only reflects the explicit information that was given to us and not anything implicit in the mind of the programmer. And that's where we'll start next time. So I'll let you guys off. So if you have any questions, feel free to come up before the other class pours in, and we'll see you on Thursday.